kedves vendégek, foglalják el a helyüket. Okay, so let us continue our program of the morning. Our next speaker is Alessio Figalli from ETH Zurich. And let me just give a very brief introduction. So Professor Figalli got his PhD in Pisa in the Scuola Normale Superiore in 2007 under the supervision of Luigi Ambrosio and Cedric Villani. In 2008, he was appointed as Professor Adamard in the École Polytechnique, and in 2009, he moved to the University of Texas at Austin, where he became full professor in 2011 and R.L. Moore chairholder in 2013. In 2016, he moved back to Europe, and since then, he is a chair professor at ETH. He also serves as a director of FIM, Forschungsinstitut für Mathematik in Zurich. Among the several distinctions over the years, he received the AMS Prize, the European Math Society Prize in 2012, and the Fields Medal in 2018, according to the laudation of the latter for his contribution to the theory of optimal transport and its application to partial differential equations, metric geometry, and probability. It is our extreme pleasure to welcome Professor Figalli in Budapest. This is not the first time he visits the Academy, and he's also running a joint book project with Professor Beretsky from the Rainy Institute. The title of his talk today, you can see on the screen, Exploring Stability in Geometric and Functional Inequalities. Please.
Thank you. So, thank you very much. Thank you very much for the introduction. It's a real pleasure for me to be back here at the Academy and also to celebrate the anniversary of the Rainy Institute. So in this lecture, I would like to kind of discuss a topic which is very broad and on which I've been working a lot, but I will try to give a sort of perspective on what you can do when you study geometric inequalities, functional inequalities, and in particular their stability. So I will start a few years ago with Euler. So Euler in 1744 wrote an important manuscript where he started to discuss for the first time how to study the isoperimetric problem. So Euler used very geometrical techniques to do that, and he is considered one of the founders of the calculus of variation, which is about minimizing some functionals with the idea of finding, for instance, optimal solution between joining 2 points, doing it the shortest time possible, and so on. So one of the classical questions that Euler was looking at is something of the following form. So you have some function y of one single variable x. So what you see on the bottom is the graph of y that represents, in this case, a curve. And what you want to do is that you have an energy represented here by a function capital Z. And what you want to either, let's say, minimize or maximize this energy. So the classical example of possible problem in the calculus of variation is the following. You have 2 points A and B. You take a particle with mass and you put it at position A, and you want to draw a curve so that under the action of gravity, the particle will reach the point B in the shortest possible time. So this is one classical problem in the calculus of variation. So when actually So when he solved this problem, this is called the Brach-Histogram problem. Euler actually used for the first time a simple instance of what we currently know in mathematics as the Lagrange multiplier method. So why I'm mentioning Lagrange? Because Lagrange enters now in my next slide. So in 1755, so roughly 10 years later, the Italian mathematician Lagrange, people forget that he's Italian, despite actually his name is Lagrangia, not Lagrange. He wrote a manuscript that he sent to Euler, explaining a different method to solve minimization problem in the calculus of variation. And he is the one who called this technique the technique of variations. So what we currently do as mathematicians. So we take a minimizer, we perturb it, so we do a variation, and we try to find optimality condition, and through the optimality condition we get the shape of the minimizer. So Euler, once he read what Lagrange did, was actually extremely impressed by it. He mentioned that despite the fact that he had meditated for a very long time how to solve in the right way these problems, it's only through the work of Lagrange that he only focused on analysis rather than geometry that found the same solution as Euler found, but in a better way. And in fact, Euler immediately dropped his original method to solve these problems, so his more geometric tools. He embraced the one of Lagrange, and then he renamed the subject calculus of variations. So calculus of variation really starts in the middle of the 18th century by this joint collaboration of Euler and Lagrange that has been so fundamental for all of us. So what is the calculus of variation? What are the problems that you study? So in general, you have functionals, and you want either to minimize or to maximize these functionals. And there are a lot of examples. And let me mention now two classical examples, because these are the ones that I will use as a motivating example of problems where you want to understand their stability. So the classical one, the supersymmetric inequality. So also, again, in honor of first work of Euler. And then more recent one, the Minkowski inequality. So what is the basic question that you have in a problem in the calculus of variation? So you have an energy. Let's say I want to minimize. And then the first thing you want to do is to find the minimizers. So you want to find the best possible solution. Next, assuming that you solve question 1, you can go to question 2, which is, are minimizers stables? So this means that, let's say you have some energy, and you have your space of competitors. The competitors could be functions, could be sets, and you know that the function of the set you're considering is not a minimizer, but is almost a minimizer, which means that energetically it's almost optimal. And then your question is this energetically almost optimal object very close to the real minimizer? So this is what we mean by stability. So could it be that just allowing a very small error in the energy, could I be completely off? Or do I still need to be very close to the optimal shape? So this is what we mean whether a problem is stable or not. And this is, of course, very relevant even for physical applications, because unless a physical system is stable, it means that you will never observe real minimizers. So the goal of this talk is to analyze this question in two different situations, which I already presented before, the case of isoparammetric inequalities and the case of the Minkowski inequality. So let's start with the first part, isoparammetric inequality. So what is that? You have a bounded smooth domain in a Rn, so a nice object, and then we know that the perimeter controls the volume. So here is a picture. I have my set E depicted there. Nu of E will denote later the unit outer normal. And then the supersymmetric inequality tells me that the perimeter is larger than a dimensional constant. So the first term, n times the volume of the unit ball to the power of 1 over n. So that the first two terms that you see after the greater or equal are just a dimensional constants. And then you have the volume of the set to the power n minus 1 over n. So this is the natural power, just because perimeter, when you dilate a set, the perimeter scales with power n minus 1, the volume scales with power n, so you need that to make the problem homogeneous. So you have this inequality, and this inequality is sharp, because if you test the inequality on balls, you get equalities. So Euclidean balls satisfy equality, and in addition, balls are the unique minimizers. So not only they attain equality, but there is no other set that attains equality except balls. So motivated by this, so this is, as I mentioned, the first step in the calculus of variation. We have a variational problem. We want to minimize, and we want to find the minimizers. So this first slide gives us the answer. And then the stability is the following. If I have a set which is almost a minimizer, what does it mean? It means that in my isoperimetric inequality, there, yeah, that one. In my isoperimetric inequality, should I move it like this? Ah, yeah, sorry, I should just point to the screen there. Okay, sorry. Yeah, so I have my isoperimetric inequality here, and I assume that I have a set which is almost a minimizer, which means that almost attains equality, and then I want to say, is it true that E is very close to a ball? Ideally, with estimates. So let's try to discuss this. So the first thing I'm going to do is to rewrite my isoperimetric inequality in a slightly different way. So the isoperimetric inequality can be written in the following form. So if you define delta to be the quantity on the top, so I just took the isoperimetric inequality and I wrote it as a ratio, then the isoperimetric inequality just means delta greater or equal than 0, and then delta is 0 if and only if it is a ball. So the delta is slightly nicer than writing the isoperimetric inequality in the other form, just because delta is scale invariant. So if you take E and you dilate it, delta doesn't change. So this is just a scale invariant way of writing the isoperimetric inequality, delta greater or equal than 0. And so our goal is to say that if delta is small, then E should be close to a ball. To measure closeness to a ball, we used a very classical notion of distance to the ball, which is the symmetry index, which is just what you see in the picture there. So what do? You take your set E, you take a ball BR of X of the same volume, and you choose X, the center of the ball, so as to maximize the overlap. So you translate your ball in such a way that E and BR of X overlap as much as possible. And then you measure how much air volume they don't have in common. So the dark blue zone that you see there. So that's the asymmetry index. So it's just measuring the lack of overlapping between the two sets. So in particular, this asymmetry is 0 if and only if E is a ball. So the question now becomes, does the deficit control the asymmetry? More precisely, can I find a constant C depending on dimension and exponents alpha, possibly depending on dimension, such that the asymmetry is bounded by constant times the deficit to the alpha? So this will tell me in particular that if delta is small, the asymmetry is small. And then if delta is 0, the asymmetry is 0. But it's a stronger result. So this is a question that has been investigated for many years, actually more than 100 years, if you consider the two-dimensional case. And people quickly realized that alpha cannot be too large. So you immediately check by a simple example, just by considering two-dimensional ellipsoids, that alpha cannot be larger than 1/2. And you see it in this example. So you see the picture. There is an ellipsoid which has axis 1 plus epsilon and 1 over 1 plus epsilon. And then in this case, the deficit goes like epsilon square. The asymmetry goes like epsilon when you overlap with the ball over this one. And so for an inequality like the one on the top, so for, oops, I just skipped slides instead of pointing, sorry. Yeah. So for this inequality on the top to be true, the exponent alpha there can be almost 1/2. It cannot be larger than 1/2. So for a long time, people conjecture is 1/2 the sharp one, and this problem has been solved in the last 15 to 20 years with a series of different proofs. The first result is due to Fusco, Maggi and Fratelli in 2008. A new result has been given by myself, Maggi and Fratelli. A new proof was given by myself, Maggi and Fratelli in 2010, and then an alternative proof in 2012. All of them give the stability result with alpha equal 1/2. But I will now present the proof that we gave in 2010 because it has also some extra features that are useful in several situations. So let me explain to you the proof. So if you want to prove stability, you need first to be able to prove the inequality itself. So stability is stronger than proving the inequality, right? So I want to prove, so proving that the deficit controls the symmetry in particular implies that the deficit is non-negative, which means that you have to know how to prove that the supersymmetric inequality holds. So the step 0 of every stability proof is, how do I prove the inequality? There are many proofs of the supersymmetric inequality, but there is one proof which is particularly elegant and actually works rather well then for stability, which is a proof due to Knote in the 50s. So Knote, I will describe this in a second. So Knote found a very elegant proof in the 50s about of the supersymmetric inequality. In the early 80s, Vitaly Milman and Misha Gromov rediscovered the proof without knowing initially that Knote already wrote it, so they found again the same proof. They were planning to write it, and then they realized that Knote had done it already. And then at that moment, around that years, Vitaly Milman was editing a book, and then as an appendix, Gromov wrote the proof, just because I think they felt that it was a bit lost in the literature. But now, for whatever reason, people tend then to call the proof Gromov's proof, while Gromov's intention was just to, make it more known to the people rather than claim any originality there. So I will call it Knote-Gromov's proof. To give credit, of course, also to Knote, but yeah, I cite Gromov as well because that's also how it's known, and of course, he made it known to a large community. So what is this proof? The proof I will present you is a slightly modification, but essentially the idea is that one. The idea is that you have a set E, like in the picture, and then you have your optimizer. You know already what it is a ball. And then you want to find a way to transport the set E to the ball. So you want to find a map T from a Rn to a Rn that deforms E to the ball, and you should do it in a good way. What do I mean by that? So imagine that your set E carries with it a density, a uniform density. So just the uniform probability measure on E, the F that I wrote on top. Then B1 carries itself a probability density, which is just the uniform probability density inside the ball. And then the way we transport E to B1 is by looking for a map T that transports the probability density F to the probability density G. Okay, so transporting a density, just you should think of it like you have your density like is a distribution of sand, right? So your probability density just represents some mass, and you're just taking the mass and transporting it from inside E to inside B1. And you want to make sure that the constant density is transported to constant density. Now, there are infinitely many ways to transport a density to another density, so there is no uniqueness there. But if you use a theory which is called optimal transportation, you know that there is a better way to do it, which is to use a map T, which is the gradient of a convex function. So this is a theorem due to Jan-Brenier that tells you that there exists always, so if you give me two probability densities, I can always find a convex function phi whose gradient is a transport map between F and G. So you don't need to know anything here about optimal transport, you just need to know that such a phi exists. And that's everything we're going to use. So now I have this map T, and then T satisfies three properties. So the first property, number one, is that the modulus of T is less or equal than 1. So this is easy just because T is a map that transports every point in E inside the unit ball. By definition, the unit ball are the set of points which are distance less than 1 from the origin. So T of X at each point has norm less or equal than 1 because it's a point of the unit ball. Now, property 2, it tells you that the determinant of the gradient of T is constant, and it's a number related to the ratio of the two volumes. And this is the transport condition. So the transport condition, I told you, I'm taking a map T that transports constant density inside E to constant density inside B1. So transporting a density, keeping them constant, it means that the Jacobian has to be constant by the change of variable formula. And the only possible constant is the one you get there. So that's number 2. So number 2 is just the transport condition. And then number 3 is a property which is specific now of our transport, is the fact that our map comes from the optimal transport theory, which is a relation between the divergence of T and the determinant of grad T. So I will explain in the next slide how you prove that, but if you accept the validity also of property 3, then you can just prove the isoperimetric inequality in 2 lines as follows. So you write the perimeter of E as the integral over the boundary of 1. Then by property 1, the number 1 is larger than the modulus of T. Then the modulus of a vector is always larger than the scalar product between the vector and the unit normal. But then once you have this scalar product, you recognize in that term, in this term here, you recognize the flux of T through the boundary. And so you can apply Stokes' theorem to rewrite as a divergence. And now once you're there, you have property 3 that allows you to replace divergence with determinant. And then once you're there, you have property 2 that tells you that the determinant is constant. You plug in the value of the determinant and you get what you wanted. So you see it's a very short and elegant proof. So what is beautiful here, so I still have to show you why 3 is correct, why property is correct. But if you accept that, you see it's a very elegant proof, not only because it's short and beautiful, I think, but also because it's actually very useful if you want to prove stability. Because essentially, stability means what? So delta small means that the perimeter, which is the first term of my chain of inequalities, it's very close to the last term in my chain of inequalities. So in particular, delta controls the gap in each inequality. So each time I applied an inequality, how much this equality is close to an equality is controlled by delta. So essentially, delta small will tell me many things. It will tell me, for instance, that the modulus of T is close to 1 on the boundary. It will tell me that the divergence is very close to the n times the determinant. So it tells me a bunch of properties on the transport map. And this is then useful because the goal in the stability will be to prove that this transport map is very close to the identity map, because you want to prove that your set E is very close to the ball. So you want to prove that T is almost the identity. So essentially, you want, through this chain of inequality, you want to deduce in reality that T was close to the identity map. So let's discuss property 3. Property 3 comes as follows. So since T is the gradient of a convex function, the gradient of T is the Hessian of phi. And the Hessian has no negative eigenvalues because phi is convex. And now you notice that the divergence of T is nothing but the sum of the eigenvalues of the Hessian that you can write in the following way. You multiply by n and by 1 over n, inside, outside. And now once you look at this expression, you see an arithmetic mean on numbers, which is going to be greater or equal than the geometric mean, because the numbers are non-negative. And the geometric means of the eigenvalues is the determinant. So that's it. So this is the proof, and it's very robust. So in particular, if you replace the perimeter with a different surface energy, so you put some function f, little f of the normal, so this becomes like what we call an anisotropic perimeter, then you still have what we call the Wolff inequality. So we have an analogous here of the isoperimetric inequality, you see. The F perimeter controls the right-hand side, which looks exactly like in the isoperimetric inequality, but now we don't have B1 here in the volume, in the constant. We have a new set kappa, and kappa is the unit ball for F star. F star is the dual norm of F. So F is a convex function. You take the dual, the homogeneous Legendre transform. So f is a one homogeneous convex function. You take f star like the dual norm, like if you think in a Banach space sense. You have a Banach space, you take the dual Banach space. You take the ball in the dual space, and kappa is, is the analog of the ball. So the proof that I just gave you works identically for this case. And then it can be used to prove stability, not only for the supersymmetric inequality, but also for the Wolf inequality. You can prove the same kind of stability result. So this is one situation where stability holds. And notice this nice power 1/2 that appears. Now let me show you a different problem, the Minkowski inequality, which is also a very classical inequality in convex geometry. And here I would like to present it mostly because it's a problem which is very rich, and you will see that techniques that apply in one situation don't apply in another, and so on. So let me start with a baby version of Minkowski. So Minkowski is about addition of sets. So the baby version of Minkowski is just the following. You give me a Borel set A with positive volume, and then you just define the semi-sum of A with itself, which just means you take all convex combination. So you fix a parameter T in 0, 1, and you take all convex combination with weight T1 minus T of points in A. Okay, so this gives you a new set that we denote by T capital A plus 1 minus T capital A. So this is all, so you take any pair of points A prime in A, and then you take all points of the form TA plus 1 minus TA prime, and you look at this new set. Now, notice that I can, in my choice of A prime, I can always choose A equal to A prime, in which case this convex combination is just A itself. So I get back all my points. So for sure, my set TA plus 1, so this set, this semi-sum, always contains A. Therefore, the volume will always increase. So this is an easy inequality. And now you can ask yourself, what can I say if I have equality? Okay? So what does it mean? It means something very precise, right? So I have a set. Consider, for instance, T equal 1/2. You have a set, and you start to add to the set all the midpoints between any couple of points on the set. And you know that when you do this operation, the volume does not increase. And then you ask yourself, can you say something now about the set E, A? So what about equality? Well, it turns out that equality holds if and only if A is convex, which is not totally obvious, right? Because convex means that every time you take 2 points, the segment is in between. Here I'm just telling you every time you take 2 points, the midpoint is in between, in the sense of measure. So it's not totally obvious, but it's not super difficult either. So convex between, convex, we have to explain what I mean convex here, because there are always sets of measure 0 that you have to be careful about. So more precisely, equality holds if and only if the following is true. The convex hull of A has the same volume as A. Or equivalently, if you take the volume of convex hull of A minus A, you get something of volume 0. So for instance, if you take a ball and you remove a set of measure 0 from a ball, this is an equality case. So you can always remove sets of measure 0. But you cannot add them. So if you take a ball and you add 1 point outside the ball, so a ball plus 1 point, this will not be an equality case. Because when you do the semi-sum, the point outside with the ball, the semi-sum will add something in the middle, which will have positive volume. So it's not symmetric adding or removing points. You can remove points, but you cannot freely add points. So this is the exact equality case. And then this is actually a very particular case of a much more general inequality, which is called Minkowski inequality. So what is Minkowski? Minkowski is the same as the semi-sum, but now when the sets are different, not anymore the same set. So you take 2 sets now of positive volume, A and B, and now you consider these combinations TA plus 1 minus TB, where little a is in capital A and little b is in capital B. And then Minkowski is an inequality that relates the volume of this set to the volume of A and B. More precisely, this is the inequality. So you take the volume of TA plus 1 minus TB to the power 1 over n, and this is larger than the T times the volume of A 1 over n plus 1 minus T volume of B 1 over n. So there are all these powers 1 over n appearing. That's part of the problem. I mean, it's part of the, it comes from the structure of Minkowski. And actually, you can check, for instance, that you have equality if you put, for instance, bolts. So if A and B are bolts, you see immediately why the powers 1 over n have to be there. So now you can ask equality there. So what about equality? So for Minkowski, equality holds if and only if A and B are homothetic convex sets, again, up to sets of measure 0. So what does it mean? Well, we know what it means to be convex sets, and we know, so what does it mean homothetic? Homothetic means that you can obtain one from the other by a translation and a dilation. So they are the same convex set up to a translation and a stretch, and dilating them. So this is the precise statement. You can find 2 parameters alpha and beta, and two vectors v and w, and a convex set in Rn, such that A is contained in alpha kappa plus V. So you take kappa, you dilate it by alpha, you translate it. You do the same for beta and W. And then up to sets of measure 0, A is the same as alpha kappa plus V, B is the same as beta kappa plus W. So you see, it's just a generalization of the previous statement when A was equal to B. So now, given this statement, the question comes about stability. So Minkowski is actually a very general inequality. Let me just mention that it appears in a variety of situations, but also is an inequality which is very strong. In particular, Minkowski implies the superperimetric inequality. So if you know the validity of Minkowski, you can just prove directly the superperimetric inequality. There is a very simple way of going from one to the other. But then the superperimetric inequality actually is the father of other inequalities, like Sobolev inequalities, Gagliardo-Nirenberg inequality, and so on. So this is just to say that this is just there is a big family of inequalities that are very relevant in geometry, in analysis, in probability, and so on. And Minkowski is now at the top of this chain. So let's discuss the stability question. So to discuss stability, it's better first to rewrite Minkowski in a better scaling invariant way. So we don't like too much these powers 1 over n around. They're very annoying. So what you can always do is the following. If you give me 2 sets A and B, you can always dilate them, both of them, by different numbers to ensure that they have the same volume. So perhaps you scale one by a parameter and the other by a different parameter. Now, if you do that, you have to change the T in the semisum. So if you look at the definition of semisum, here. So if you have 2 sets A and B, you're looking at convex combination with these 2 parameters. Now, if you dilate the set A by lambda and you dilate the set B by mu, then if you want to obtain a set, so if you want to make sure that the new set TA plus 1 minus TB is just a dilation of the original set, you need to change the T in terms of lambda and mu. So if lambda is different from mu, the T will change. But up to playing with T, you can always ensure that the 3 sets don't change in shape. So you just dilate one, you dilate the other, and then the third one gets dilated provided you change the T accordingly. So the advantage is the following. You can always reduce yourself to the case where A and B have volume 1 now. And of course, because the role now of A and B becomes symmetric, you can always assume that T is less than 1/2. So T is a number between 0 and 1. You can always assume that is less than 1/2. And so let me write now the Minkowski inequality. Minkowski inequality now it just becomes this. TA plus 1 minus TB greater or equal than 1. Because if you remember what it was before, let me go back just to convince you. Here. Sorry. Yeah. So when A has volume 1 and B has volume 1, you see the right-hand side is just T times 1 plus 1 minus T times 1, which is 1. And then saying that a number to the power of 1 over n is greater or equal than 1 is equivalent to say that the number is greater or equal than 1. So I can, in this way, I got rid the right-hand side became 1, and in the left-hand side I can read of the power. So that's the advantage. So this is now Brun-Minkowski. And now I can formulate stability. Stability is the following. Let's assume now I have a deficit, so this delta t of A and B. So it's a deficit that depends on three things: A, B, and the parameter t. Because it appears there is also a t in the problem. So let's assume that this delta t is very small. Question, is it true that A and B are almost convex? And they're actually close to the same convex set. And perhaps can we do it in a quantitative way, right? So remember, equality in Brun-Minkowski is the following. If delta t is 0, then A and B are convex and A and B are homothetic. Now we want to say if delta t is small, A and B are almost convex and A and B are almost homothetic. So this problem, as I just stated, has two statements in it, this stability question. There is the convexity and the homotheity issue. So the first thing that we would like to say is that the error in Brun-Minkowski controls how far A and B are from their convex hull. And then the homotheity part, we would like to say that the error in Brun-Minkowski controls the difference between the shape of A and the shape of B. So this is what we want to do, right? We want to solve both convexity and show that both convexity and homotheity holds in a stable way. Now, when we started working on this problem more than 15 years ago, of course we had no clue how to do any of this. And then we took the following approach. So here I have two things to prove, right? So I need to, just with error Brun-Minkowski, I want to control convexity and homotheity. I could try to simplify my life by doing the following. Every time I try to solve one of the two, I'm going to assume the other to be true already. Let me explain. Let's look at the convexity issue. I want to show that the error in Brun-Minkowski controls how far A and B are from the convex hull. That's what I want to show. Let me assume that the homotheity is already true for free by just assuming A equal B. They are the same set. So, you see, I have a problem. I have no clue. So I have two problems to solve. I don't know how to solve them. So I'm going to make the conclusion of one of the two as my assumption, and I try to solve the other. So the second case will be the homotheity issue. So I'm going to assume that the sets are convex, and I want to prove that they're almost homothetic. So there are the two things. This will not, of course, solve the general problem, but if I'm not even able to do the basic easy problems, I will never be able to do the general problem. One has to start from something. So that's what we did. Actually, we started from the homotheity question. So we said the homotheity issue. So we are going to assume that A and B are convex, and we're going to prove that A and B have almost the same shape in terms of delta. And then the convexity issue, we're going to assume A equal B, and we're going to prove that A is close to its convex hull. And then finally, we're going to try to understand if we can do something in the general case. So let's start with homotheity. Let's assume that we have two bounded convex sets. So you see convex is an assumption of volume 1. I'm going to define a distance as before, just the overlapping distance. Right? You take the two sets, you translate them so that they overlap as much as possible, and that's your distance. And then the theorem we could prove in 2009 with Maggi and Pratelli is the following, that the deficit in Brun-Minkowski controls the distance between A and B. And you see there is still a power 1/2, and then in front there is a constant, which is actually has a very special structure. It's a dimensional term, C of n, times a t to the power 1 minus 1/2. So the constant in front blows up as t goes to 0. And let me just mention that this is all optimal in every sense. So the power 1/2 is optimal. Ellipsoids, just you test it with two ellipsoids and you see that it's optimal. And the t to the minus 1/2 is also optimal. So as t goes to 0, delta, as t goes to 0 exactly, you need exactly t to the minus 1/2 in front for this inequality to be true. And the constant is also explicit with some polynomial in n. So this was, let's say, actually, it turned out to be a very easy case, I should say. So the proof is not very complicated. It's again based on optimal transport, as in the isoperimetric case. And actually, it's even easier than the isoperimetric case, because we're assuming A, B to be convex. Now, let's move to the other one, which is more interesting, the convexity issue. So the point is this. Now, suppose that I want to drop the convexity assumption. And it turns out that the moment you drop the convexity assumption, the proof of Minkowski just using optimal transport just completely fails. I mean, you cannot use it to get any stability. And in general, you need a new strategy now for convexity. So actually, it's not surprising. Let me just say why. Because in the convexity issue, remember what you want to do. Let me go back just to make sure that, yeah, convexity issue. Assume A equal B, prove that A is close to convex hull. So if A is equal to B, the transport map from A to B is just the identity map, because I'm just transporting A to itself. So there is no information in the transport map, because the identity map carries no information. So clearly, if I want to prove that A is almost convex, I need something else. It cannot be in the transport map, just because the transport map is trivial. So I need something different for the second part. And optimal transport, there is nothing to do. So to understand this problem, let's just consider a very simple case. Dimension 1, t equal 1/2. So I have now a subset of the real line, A. Let's say that A is Lebesgue measure 1. And let me define the deficit in this case with t equal 1/2. So you take the set, you do 1/2 plus 1/2 of itself, and you subtract 1. And then the question is, can I use delta 1/2 to control how far A is from the convex hull? Right? I'm just re-saying the same thing, but just I want to make sure that we are all on the same page. Okay? And now the answer, so if you just ask, does delta 1/2 controls the volume of convex hull of A minus A? The answer is no. And this is the example. On the real line, so think I'm on the real line, and my A consists of two intervals of length 1/2 very far away. So you just take on the real line two intervals, and you put them far. Now, when you take the semi-sum of two intervals, you will get three intervals. Just the two original ones plus an interval in between with length 1/2 as well. So the volume of the new set is 3/2. 1/2 plus 1/2 plus 1/2, right? So I have 1/2 plus 1/2 plus 1/2. So this is 3/2, minus 1 is 1/2, so that's the deficit. And now the convex hull of A can be huge, just because the intervals are far. So you see, delta cannot control the volume between convex hull of A minus A, because one is just always 1/2, and the other one, I can send it to infinity. So this looks like bad news. It looks like I cannot prove anything. And as we were trying to understand this problem, I was actually at that time visiting UCLA, and I was chatting about this one day with Terry Tao, and then I mentioned, oh, you know, when you do this Minkowski, you do semi-sums, you have this kind of strange phenomena. And then Terry told me, oh, yeah, but that's just, you know, the degenerate case, because otherwise you can apply Freiman theorem. And I had no clue at that time what Freiman theorem was. And I asked him, what is Freiman theorem? I don't know it. And said, oh, yeah, it's in my book on additive combinatorics. Open that page, whatever, 200 something, and you will find it. So I took his book in additive combinatorics. I looked at the statement. It was a statement about arithmetic progression on Z. But then when you think, okay, perhaps if I think that Z, if I take Z and I start to shrink it, so instead of having at the integers, I just put points of Z at very close by distance, and I approximate real numbers with Z's, with just multiple of Z's, then in fact it makes sense. I can just take the statement for arithmetic progression, pass to the limit, and get a statement here. And Freiman theorem which is a very classical result in additive combinatorics. When you look at it on R, just will tell you this. Take a subset of R of volume 1, and let's assume now that delta is strictly less than 1/2. So just kill this example. This example here, just kill it by assuming that the delta is small enough, and by small enough, I just need strictly less than 1/2. Then you have this beautiful simple inequality. The volume of convex hull of A minus A is bounded by twice delta 1/2 of A. And that's it. The best stability you can hope for. Notice you have a constant in front, 2, which is optimal. And you have delta to the power 1 in this case. Even better, not even power 1/2. So I have a linear control. Delta just tells me how close I am to the convex hull. So actually, Feynman theorem is much more general. It's about additive subset of Z. And actually, there is a Feynman version also when you have A and B different sets, so that you can apply essentially to prove stability for Brun-Minkowski in one dimension. So if you're interested in stability for Brun-Minkowski in one dimension, everything comes directly from Feynman's. Of course, this is only 1D, and there is no analog in higher dimension. I mean, the parallel just breaks down completely. So if you go to higher dimension, now you are a bit more encouraged by the fact that you know how to do it n = 1, but still you need new techniques. So let me focus again on the case where the sets are the same. So A now is a subset of Rn of volume 1. T is between 0 and 1/2. Delta T is just that quantity. And now, you want to prove that delta T controls how far you are from a convex hull. So the first result is due to Mike Rist, 2012. And what he proved is that as delta goes to 0, the volume of the convex hull of A minus A goes to 0. So this is like a qualitative version, which is already non-trivial. So very often, these kind of qualitative results are very easy by compactness. This is a highly non-compact problem because convex sets are not compact. The family of convex set is not compact. So this is not so easy. Then there have been further work, first by myself and Jerison, and then the conclusive result is due to Van Intum, Spink, and Tiba, where they prove, and the final statement, which is true now in every dimension, tells you that if the deficit is small enough, then you have a stability result, which is exactly the same as in Feynman. You have a t minus 1, delta t to the power 1, and the dimensional constant. So in every dimension, the delta controls linearly convex hull of A minus A, and you have a parameter t to the minus 1 now. Minus 1 is sharp because here is power 1. And you have a dimensional constant, and everything is sharp here. So in particular, it shows the stability, but everything is optimal. Now, if you now move to Brun-Minkowski, you have the general case, which we recently solved. And what this says is essentially the generalization of what I already stated for you in the convex case. And it tells you the following statement. So if delta is small enough, then you can find a convex set such that up to translation, A and B are the same convex set. And you see again in the right-hand side, the t to the minus 1/2 and delta to the 1/2. So you see, the power 1/2 is again needed. So in the general case, this is needed because this result has to include in particular the result of when A and B are two different convex sets. So again, two ellipsoids will show you that the power 1/2 is needed. But the funny part is that if you just focus on the convex part, so how far the set is close to its convex hull, you need power 1. If then you want to show that the two sets are similar, you need power 1/2. So there are two different behaviors in these stability estimates. In fact, we do prove linear behavior. So we prove also in the same paper that if you're just interested to show that A is close to a convex hull and B is close to its convex hull, then you get linear power. But then you get power 1/2 once you want to show that the two sets are homothetic. So it's the homotopy part that gives you power 1/2. It's not the convexity issue part. So this is a bit the kind of overview I wanted to give. Just I showed these two examples are interesting, I think, because they just show how different techniques interact. And so they're very different techniques, right? So if you try to study a supermetric inequality or the Brun-Minkowski inequality for convex sets, then you need to use optimal transport works very well. If you try, for instance, to prove stability for Brun-Minkowski in dimension 1, then additive combinatorics is like the tool there. And then if you try to do Brun-Minkowski in higher dimension, I didn't explain the ideas, but it's really an interplay of many techniques: combinatorics, geometric measure theory, analysis, and geometry. So there are many tools involved. So it's a very rich family of problems, also in terms of the techniques you need to develop. And I would like just to conclude this overview with also some perspectives of direction. So, of course, you can take this line of research and take it to many inequalities. There are many inequalities in the setup of analysis geometry. You could ask, are these stable? Are they not stable? Can you prove sharp stability? And so on. But there's also another setup which is interesting, which is about critical points. So instead of asking yourself, is a minimizer stable? I could ask, are critical points stable? So I'm not assuming anymore that I'm optimal in energy, but I'm just going to assume that I'm almost a critical point. And let me give an interesting example. So a celebrated result by Alexandrov tells you the following. Let E be a smooth bounded set which has constant mean curvature, then E is a ball. So this is a result from the 1940s, very classical. There are many different proofs of this result. And this result is the critical point version of the supermetric inequality. Because if you have a set, so if I don't tell you that the minimizer of the supermetric inequality is a ball, what you could do is the following. You take the supermetric inequality, you prove that a minimizer exists, or you assume it, let's say, and then you write down the optimality condition for a minimizer, the Euler-Lagrange equation. So you take a minimizer, you perturb it, and you try to check what it should satisfy. And it turns out that every critical point for the supermetric inequality will be a set with constant mean curvature. So constant mean curvature is the Euler-Lagrange equation of the perimeter with fixed volume. And so a minimizer of the supermetric inequality is always going to be a constant mean curvature surface, and then the unique set whose boundary has constant mean curvature, the unique bounded set, connected, otherwise you can take union of balls. I should have added connected. The unique bounded connected set with constant mean curvature is a ball, okay? Which then is the solution of the supermetric problem. So this statement, the Alexandrov theorem, is the analog of saying that balls are the unique minimizer of the supermetric inequality. Here I'm telling you the balls are the unique critical points for the supermetric inequality. And then you could ask, take a set which has almost constant mean curvature, in any sense you want, mean curvature equal to 1 plus a very small perturbation. Is it true that E is almost a ball? And here, something very interesting happens, and this is the, I just rewrote it. Here, something very interesting happens, and what happens is the following, that you have this set, which is made of two balls connected by a small neck, and this set is, you can do it in 3 dimensions, so in 2D you cannot, but in 3D you can add curvature in the neck, and in this way, you can find a set which has mean curvature extremely close to a constant. So you can find, this is a phenomenon which is called bubbling. So you can find a set whose mean curvature is close to 1, but is not a ball. It's 2 balls. So there are this new phenomena that appears, because now the energy doesn't prevent this existence of multiple balls. And so proving stability already in this setup, sharp stability is still open, actually. So there are partial results with non-optimal powers, but it's still open. So one needs much more, one need to develop new techniques, and it's actually a very interesting line of research as well. So that was everything I wanted to say, so thank you.
So can you take this last perspective a bit further in the sense that you want to get stability for differential equations, or maybe partial differential equations through this framework, and is it meaningful?
Yes, so you can take this idea also to PDEs, right? So the first example could be the Sobolev inequality. So you take the Sobolev inequality p equal 2. You take the critical points. So this is minus Laplacian u equal to the u to the 2 star minus 1. And then you could ask, if I'm very close, can I prove Shah stability? And the answer, so the case, currently the case of Sobolev p equal 2 is the only one for which we have the result. But it's interesting because then the result depends on dimension, which is something you don't see for the minimizers. So minimizers have always this power 1/2, usually, or 1/2, whatever. Like if you do for critical points, the power, for instance, for Sobolev is 1 up to dimension 5, 3, 4, and 5. In dimension 6, you have a log. In dimension 7 on, you get a different power depending on dimension. And these are all sharp. So you get new phenomena, and this is due again to bubbling, because so you will have solutions of PDE which are made like, so let's say you have a solution to a PDE which is some profile. You know that the exact solution of PDE has a very precise profile, but now you could have a normal solution which is made of 2 profiles very far away. So you just take the same solution and you translate it far. And now these 2 profiles will always interact a bit, because usually these solutions of PDE are not compactly supported, so the support will overlap. And in that region, there will be some interaction terms. And then the way they interact may depend on many things, including dimension. So you get all these new phenomena appearing. So there are results, but it's still a very recent area. So all this, to Sobolev has been done between 2020 and 2023. The 2, which is like the easiest case. So I think there is a lot to be done.
Cool, thank you.
Any other questions? Well, if not, then let's thank our speaker again. Thank you very much.